Hey there, how you doing? Welcome to the channel. So today's going to be an update on the clock project that we're working on. As you can see here, we have on the breadboard, we have two digits going. What's going on here is that they are actually counting, and these the numbers are actually coming from the real-time clock calendar inside the PIC microcontroller. So we've got that working, and so that's kind of helpful. So the other thing is I had actually done some soldering this past weekend, and I kind of was not happy with how things came out because I had to do solder bridging. It was really kind of messy. And I was kind of like, yeah, I don't know about this solder bridging stuff. And let me see if I can find that. Maybe I'll just show that. Yeah. Yeah, it's right here. It's right here. Yeah. So let's see if I can show this. Yeah, if you look here, so here I had I have a breadboard, and so I have my dips on there, sockets I was going with. And so I started, now this particular one has, you can see it's just got pads. The pads aren't connected, this pad. So unlike the breadboard, you don't have strips of points that are connected together for you. So what that means is that, you have to connect these points together. And so the way it works is you end up having to make solder blobs, as far as I can tell. And I kind of read about this, and you can see that I oriented the sockets such that I'm going to flip the chips around so that, basically the pins from one chip directly connect to the pins of the other chip. And you can see that you have to make these solder blobs. Now, these I think actually look pretty good. Like, what I was surprised because of the solder mask, like they tend to just bead up and have surface tension. So it kind of works pretty good. But I'm not really happy with it because I just kind of like, hey, look, these, like especially over here, these solder blobs are kind of like, you're prone to shorts and whatever. I buzzed them out. They were okay. But so I'm going to go with a different kind of version. That's what I'm going to do. I decided. So that'll be maybe this weekend or next week. I'll start on that. But so what I did do is I breadboarded two digits here. So if we look at what we're doing again, we have, here's the clock. Let's see, what did that do? Yeah, so here's the clock project. So once again, we're going to have this big clock here that's going to have years, months, days, hours, minutes, and seconds, because we're going to do this long-term counting. And so what we have is this PIC controller with a real-time clock module in it. And so basically what I have right now is I basically have implemented over here the seconds digits right over here. So this guy is working right now. This one here, the seconds digits. So that's what I have going right now. And what I'm doing is, if you look at the dual digit, so basically I'm trying to do like a dual digit module. And yeah, so electrically it's going to be like this. Each digit is supported with a shift register. So the data is going to come in here, enter the shift register, and then it's going to go through another shift register here. And and then the shift register outputs are clocked on our clock and then applied through this UDN 2981 that gives me the current drive I need to, drive the Nixie tube. And so, as we talked about before, we could have different mappings depending how you wire these things up. And so that's kind of the idea. Now, what I was doing is this is kind of my view of what I was doing on the previous version of the prototype board, the one I showed you where I soldered. Basically, I have this situation where, I was going to flip this chip and have this chip here. And then these would basically be solder bridges. And then I would just figure out the mapping from there. But like I said, so I'm kind of throwing that out. So that one's going to be out. And so I'll come up with a different mapping based on what I have. And I think I'm going to get boards something like this. And so what happens is you can mount the dip in there. And what will happen is you'll have room to at least have like 3 or maybe 4 connections. Well, probably 3 connections on top of that. So I can solder the dip socket in, and then I have 3 connections for putting wires to there. So I don't have to do solder bridging. I can put multiple wires in. That's okay. That's not a biggie. But I just, that'll make it better solder connection. So here I'm trying to map it out based on the size of the board. So I'm not kind of sure exactly what to do at this point. I have, you know, here's where the tube is gonna, 2 pins are gonna go in. Here's the tubes, and I'm trying to put 4 per package here. Let's see, UDN. So that looks like it works. Like I can get 4 per. So that looks like it might work. But yeah, so I'm still working on that. So when I get the new boards, I'm working on that. Yeah, so that's what I have there. And then, so let me look at it, show you the code. So one thing was the way I wired these 2 digits, I wired them differently. So let me show you that. Oh my gosh, this thing. Share this one. Yeah, so like I had shown before, up here is, you know, this is the mapping for the digits. So basically I have, if I want to put a 0 on the tube, 1, 2, 3, these are the 8-bit values that I need to shift out. And these are based on the actual pin wire connections to the tube. And this is these wires. So wire 3 on the tube, light segment C, 4 is the decimal point, 5 is B, etc. And we did this experimentally. And then over here you can see, so basically you can see, like with this particular setup up here at the top, you know, if you want to display a 3, you have to light segments A, B, G, C, D, and that would be these segments here. Right now, what happened is for the most the LSB is wired the same, so it has the same mapping. But the most significant bit of the second digits, I ended up wiring it differently. So I basically had to just, you know, figure out exactly what that is, and you basically have a different set of mapping here. So basically, when I'm shifting out to the most significant position, the tens digit, I have to map it with this map. If I'm sending out the ones digit, I have to map it with this. So that's all we did. I mean, I think obviously it will make all the mapping the same on the final product. I mean, maybe not. If there's a reason to do it differently, we can do that. But that's fine. You know, I'm just showing that you can do that, and you can see that it's counting, and so that's all cool. And so let's go over here. We're going to share. Now we're going to share the code. Yeah, so here we are in the PIC controller thing. So what I'm doing here is, you know, in my main program, let's see, what am I doing? I wonder if I still need that code. Yeah, I don't know. But here's the main loop. So you come into main, like all C programs, you enter main, right? And I have a current time structure based on what the time is. And then this enables the real-time clock. And so that was the thing I was struggling with for a long time, getting the real-time clock running. Now, this particular procedure works okay. And it's actually, this procedure isn't the problem. The problem was in the definition of the clock. I wasn't like setting the internal oscillator, so my real-time clock enable was never going to 1. And that's a common, you know, that's kind of a common thing that we'll see if like I spent years in the lab debugging like ASICs, like, I mean, really, you know, expensive high-end ASICs and stuff. And this is something that you will see. It's very common because there can easily be confusion. And it's like, how to enable the clocks? Is there a different enable? Typically they'll, you know, you want to just turn off every clock you don't need. So to get some block running, you might need 3, 4, 5 different enable bits set for just to get the clocks running. And if you don't have the clocks running, then, you know, basic read writes of registers may not work. And so that's exactly what was happening here. So that's resolved. That's all good. My interrupts enabled, but I'm not using them yet. And we'll get to there. So I just set the default value of, you know, S clock, S data, R clock in the grid. But then I go in here and I'm doing the run clock. So what I do is, you know, I basically come into this function, RTC time get, where I basically read the time from the real-time clock. So if we go to here, we go to the implementation. This is the function that they gave us. And so this is fine. One thing I do is we look for, it's like, we wait for, if RT sync is 1, then we clear it. Okay, so we want to make sure it's not syncing at that time. And you could read about this in the PIC spreadsheet. But basically, it's just going to give you a structure. And that structure, you know, has the year, minute, day, the whole deal. And it returns it to us. And so what I'm doing here in C, what am I doing? Current time now is, so yeah, so what I do is the return value says whether I successfully got it or not. So basically when I come into here, I say, okay, I didn't get it, it set it to false. And then, so basically if it has to read it a few times, it'll keep reading it until it says true, meaning that it's actually got a time value to make sure I have a time. And then my current time is just going to be a structure. It's the same structure they gave us in the code over there for the real time. It's a structure of a TM type, which has all those fields. And then what we're doing is we do end up having to convert it from hex to BCD. So basically this time value in seconds is a hex value. So what we're doing is we're converting to BCD, right? Because, so think about it. If you have a 4-bit field, so the values in there are 0 to 15. Okay, and those would be 0 to 15 represented in binary or represented in hexadecimal. But what we want to do is we don't want to just, you know, put in there, well, I'm sorry, seconds is actually an 8-bit field. I think it's an 8-bit field, right? Let's just go check that really quick. I forget. It's so funny, I just forget. But yeah, time seconds, get decimal value, current time. I think, yeah, if you go to the definition of this structure, yeah, right here. So, okay, so all these values are, and this is really good if you're new at it, if you set up in what's called an IDE like this, the integrated development environment, it just helps you out. You can just navigate much easier because when you get into big projects, it can be very difficult to find stuff. But so the point is the TM seconds is an integer. So it's actually, what would an integer be in C? By default, it should be like a 32-bit value, right? So, okay, so we get a 32-bit value. So what happens is it returns us basically a 32-bit value that we have to convert. So that 32-bit value could be from 0 to whatever, 2 to the 15, 31,000, whatever the number is, right? And actually, that's not the case. It's actually split up into two, like I think everything's not populated, so it's split into 2 digits. But the point is, it's not packed, right? It's not represented in BCD. So the point is, you have to represent it. You have to get the digits out. So basically, this convert hex to BCD. Go to implementation. Yeah, so it's a hex value, and we basically have to isolate the different digits. So basically, you take the divide by 10 is going to give you the tens digit, and the modulo 10 will give you the ones digit. And so that's how you get the 2 digits out. And then you basically just put them back. You put them back in, but now you have a digit instead of a hexadecimal. So I know it's very confusing, but basically, you know, if you have, like, within 4 bits, you could have from 0 to 15 seconds. And, you know, that's not what we want. We want, you know, to represent digits. So basically in BCD, you would have 0 through 9, and the rest 10 through 15 would just have no value, right? And so that's why we get, you know, a specific 4-bit value that we take and we send, and we take that 4-bit value, which is now a number from 0 to 9, and then we're going to basically call it, send that digit, and we're going to give it a mapping, and that mapping is going to tell us specifically what segments to light per the mapping table that we discussed. So we get the time in seconds. So what's happening every time we come in this loop, we're just going to grab the time, and we're going to grab just the seconds. I'm just doing the seconds. And well, here I'm grabbing the minutes, but not doing anything with it. So I'm grabbing the seconds. And then what I'm doing after the output of this function is I'm basically taking the ones digit. So what I'm doing is this, it's a 32-bit value. And you got to take out the only the lower 4 bits. That's the ones digit. And then you want to take out over here the tens digit, right? but see that you want to isolate it. That's what the value is, those 4 bits, and then you want to shift it over so it's right justified. So that then that digit is, so basically if it was 223 seconds, you would get a 2 here up in this position and need to get a 3 here. Well, you need to just shift the 2. You don't want to shift 20 out. You see what I mean? So that's why you just right shift it like that. You send your digit out. Now what I've done is I've send digit with no R clock. So because now I have to send 2 digits. So noting here that my digit on the right, the seconds digit, is the second group of 8 bits. Okay, so I send that one first. I send the ones digit, and then I send the tens digit, and then I pulse the right clock to write in those 2 values. Okay, and then I wait some delay. And so what's happening here, this is very inefficient. I'm pulling, and I'm just sampling really fast. So basically I'm sampling, I may be sampling thousands of times a second. So that's why at some point this will switch it over to interrupt code where we say, well, just send me, I think we could do an interrupt every second, but we'll probably do the interrupt like every 2 seconds. I think they have a 500 millisecond interrupt, something like that. We'll do something like that. So like all this code, the processor can just go idle, and then it just waits for the interrupt from the clock that says, hey, we're going to have to increment the 1 second time. So that's what we'll do. But let's look at here, send digit no R clock. So we'll go navigate to implementation. And this guy, so all this guy is doing what I'm supporting here, I have the digit you want to send, and I have mapping type now. So basically what I'm saying is I can do different mapping types. And so you can see here that, here's the digit I'm sending, but then the second argument is the mapping type. So the ones digit is mapping type 1, and the tens digit in mapping type 2. So now when I go over here and all I do is I go send digit, I'm going to get digit, which is going to do the mapping. I send the mapping type through. So let's look at send digit. So I have a option for send digit. If it's 0, I just pass it through. That allows me just to do testing. If it's 1, I have the original. So this would be the tens digit mapping. And then I have the other digit mapped here. Yes, which is this. So I have mapping type 0, 1. When I set it to 2, it just takes the else. Okay, so that's how that works. So it's all really simple stuff. I mean, it's all good that we have the real-time clock running. I guess I'm not sure what's next. I have to do the soldering and all that stuff. I think I have to find a way to really test the minutes and the hours digit without waiting minutes and hours. So there's something that we need to do there to test that. And then we really have to get to the point of looking at the alarms and all that stuff and how we're going to make that work. But that's kind of good. So that's where this thing is at this point. It's getting there, got digits counting. So one thing I want to show here, if we just look at our clock, if we watch this thing for a little bit, what you're going to see, hopefully, is this is going to dull out. It's going to get dim. It's going to dim out. That's what I meant to say. You see how it's getting dimmer and dimmer? You'll see it almost get totally dim. Yeah, dim, and then it gets really bright. So what's happening is right now my 1.5 volt supply is really struggling. And so what's happening is I think that regulator, that 1.5 volt regulator, which is that little guy over there with the resistors at the end, that guy's getting hot. Like if I touch it, it's like really hot. It'll burn your finger. Now, of course, that's not good, but there's a couple things going on. It should be able to handle the current from the calculations. But clearly it's not handling it right now. So the question is going to be, I think what the question is going to be, I mean, the first thing I'm going to do is obviously put a big heat sink on there, and that hopefully will resolve it, because I think it's like thermal throttling. So basically they have some kind of circuit in there probably where it like literally heats up and it just starts shutting down the current. And when it shuts down the current, the voltage drops off. And when the voltage drops off, these lights dim, and then it recovers and it's able to run and put the voltage back up at 1.5 volts again, but then it heats up. So I think it's probably just that. If need be, I'll have to go and look and adjust that, meaning that I might have to have 1.5 volt per digit, which would be a lot, but I don't think I'll need that. I think it's just a heat sink. I think this will be a lot better because I definitely saw the voltage get below 1 volt on it, so it may be just totally shutting off. All right, well that's it for this one. So yeah, that's it. Update on the clock. Bye.